Have you ever stared into a simple glass of milk and thought about, the entire universe? Yeah, probably not. But it turns out this everyday drink is actually a perfect doorway to understanding some of the most fundamental laws of physics. We're about to see how a simple purity test can reveal the secrets of matter, force, energy, and even light itself.
It's a kind of unsettling question, isn't it? But milk adulteration, especially just watering it down, is a massive problem in the dairy industry. It's a really easy way for some people to cheat the system, and it seriously damages the quality and the nutritional value of what you're buying.
And this is no small problem. I mean, look at this number. One study in India found that over a third of milk samples were low quality, and water dilution was the main reason why. That is a huge number, and it just goes to show why having a simple, reliable test is so incredibly important.
So how do you even begin to fight back against a problem this widespread? Well, you do it with this clever little device right here, the Lactometer. It might look pretty simple, but it is an incredibly powerful tool that uses some absolutely brilliant physics to tell you, almost instantly, if your milk has been watered down.
Okay, so here's our game plan. We're going to start with the lactometer test itself, how it works. Then we'll unpack the science of floating, dig into the nature of pressure, see how heat changes everything, and even look at how light lets us see the result. By the time we're done, you'll see how it's all connected.
Right, so we've got this basic glass tool. You pop it in some milk, and somehow it tells you if it's pure. But what is actually going on in there? What's the secret sauce behind this simple test?
At its heart, the lactometer is really just a type of hydrometer. Its entire job is to measure something called specific gravity, which is just a fancy way of comparing the density of milk to the density of plain old water. The real magic behind how it does that? It all comes down to a brilliant idea from over 2,000 years ago, Archimedes' principle. And that brings us to our first real deep dive into physics, the science of floating. To get how the lactometer works, we first have to understand why some things sink and other things float. And it all starts with one key concept: density.
So what is density, really? It's just how much stuff, or mass, is crammed into a certain amount of space, or volume. Imagine you have a block of wood and a block of iron, both the exact same size. The iron is way, way heavier, right? That's because its matter, its atoms, are packed together much more tightly. It's just denser. And this is where it gets really interesting. Look at the numbers. Water has a specific gravity of exactly 1. Cow's milk is a bit denser, thanks to all the proteins and minerals floating around in it. But get this, skim milk is even denser. Why? Because fat is actually lighter than the rest of the milk. When you take it out, the average density goes up.
Now, this is the absolute key to everything. When you place an object in a liquid, it pushes some of that liquid out of the way. What Archimedes figured out is that the liquid pushes back with an upward force. We call it the buoyant force. And that force is exactly equal to the weight of the liquid that got pushed aside.
So it all becomes this battle of forces. If an object's weight is more than that upward buoyant force, it sinks. If it's less, it floats. The lactometer is designed so that in pure, dense milk, the buoyant force is strong and it floats up high. But in watered-down, less dense milk, it has to sink deeper and deeper to push enough liquid out of the way to support its own weight. Simple as that. That upward buoyant force is a perfect example of pressure at work. And once you start to understand pressure, you start seeing how forces operate not just in a glass of milk, but literally all around us every single day.
At its core, pressure is all about how concentrated a force is. It's the amount of force you apply over a specific area. You could have a massive force, but if you spread it out over a huge area, the pressure is actually pretty low. But if you take that exact same force and focus it onto a tiny, tiny point, the pressure becomes absolutely immense. And you see this principle everywhere. It's why a sharp knife cuts so much better than a dull one. It concentrates all your force onto that tiny, sharp edge. It's why a nail has a sharp point, and it's why dam walls have to be incredibly thick at the bottom to handle the crushing water pressure that builds up with depth. It's just fundamental to how our world works.
But of course, there's a little catch in our simple milk test. The reading you get on the lactometer isn't always the full story. It could be thrown off by one simple thing: temperature. And this little wrinkle opens up a whole new area of physics for us to explore, the world of heat and energy.
So, what gives? Why does just heating up or cooling down the milk completely change the result of our test? Well, the answer isn't on the surface. It's deep down at the molecular level. It's all about how heat affects the tiny, vibrating particles that make up everything. It all comes down to something called the kinetic theory. Think of the molecules in the milk as a huge crowd of tiny dancers.
When the milk is cool, they're just sort of swaying. But when you add heat, you're basically giving them a shot of pure energy. They start dancing faster and wilder, bumping into each other and pushing each other farther and farther apart. The milk itself actually expands. And now you have the same amount of stuff in a larger space, which means its density drops.
Okay, so we've tackled density, forces, and energy. But there is one more crucial piece of physics we need to actually get a result from our lactometer. We have to be able to see the reading, and that brings us to the absolutely fascinating world of light.
When you look at the lactometer's scale through the side of a glass jar, the light traveling from that scale to your eye is on a wild ride. It has to pass from the milk, through the glass, and then into the air. Every time it crosses from one of those materials to another, it actually changes speed and bends. This bending is called refraction, and it's the exact same reason a straw in a glass of water looks like it's broken right at the surface.
And while refraction is all about light passing through things, light can also bounce off things. That's reflection. To really get a handle on light, it helps to see both sides of the coin. Here you can see the two main types of curved mirrors that play with reflection: concave mirrors, which curve inward like a bowl, and convex mirrors, which bulge outward.
Their different shapes make them handle light in completely opposite ways. A concave mirror focuses light to a point, which is great for magnifying things. A convex mirror spreads light out, which is why they're used for car mirrors, to give you that wide-angle view. It's just another way we manipulate light's path. But for our lactometer, the star of the show is refraction, that bending of light that lets us read the scale. All right, let's take a final step back and put all these pieces together. We started with a super simple question about a glass of milk, and it's taken us on this incredible journey through the core principles that literally govern our entire world.
I mean, just stop and think about that. That one little glass tube is a practical, hands-on demonstration of 5 huge areas of physics. You've got the matter of the milk itself, its density being the key to purity, the buoyant force making it float, the energy from heat affecting the reading, and finally, the bending of light so we can even see the result. It's all connected.
It really makes you wonder, doesn't it? If a simple glass of milk is holding all these secrets, what hidden physics is at play in your morning cup of coffee? You know, from the heat transfer that brews it, to the evaporation of the steam, and the way light refracts through the mug. The world is just full of these hidden connections, just waiting for us to see them.